Lecture 9 of an introductory class in electricity and magnetism, and this lecture introduces what's known as Gauss's law. It is a law about electric field in this case, and in particular it's really about the net electric field. So there are learning outcomes. There's two of them. One of the things you need to learn how to do is to learn how to calculate the flux of a given field through a given surface. So this surface is purely mathematical and it is not physical. That is, this surface is not made out of any material. So let me say material instead. And then the other learning outcome is once you know how to calculate the flux, it's to be able to use Gauss's law to relate electric charge and how the electric charge is distributed to a field line diagram for the electric charge and a general closed surface. And this surface is the surface that you're going to learn how to calculate flux for. So so there are some sections. So first I'm going to indicate to you how to calculate electric field flux. We'll have to, this will be pretty cool. We'll be able to define a surface with a vector, and then we'll be able to define a flux based on the surface vector as well as the electric field vector. So there's two vectors. When we define the flux, we'll also have to say when is a flux positive and when is it negative. And also address the fact that flux is a scalar quantity and it's a physical quantity. Kind of a corollary to just being able to calculate the flux is to being able to calculate the flux when the surface and the field are at various directions with respect to each other. So we'll also talk about in this video, right? This is an introduction to Gauss's law. We're also going to talk about what is Gauss's law and why do we care about it. So actually, the truth is maybe I'll put this, hopefully I copied it, after that. Sure, why not? Let's try it that way. So I'm going to describe the statement of Gauss's law, and Gauss's law has this really interesting looking equation. This symbol over here symbolizes what's called the flux. So in particular, this is the flux of electric field. And then there's charge, and then on the bottom is permittivity of free space. And then maybe this makes sense. And then we'll talk about why we care about Gauss's law. I'm going to give you two reasons, one of which is mostly what you'll do early on when you're learning about Gauss's law, is you're going to use Gauss's law, and what I mean by that is you're going to leverage this Gauss's law as a tool to be able to get the electric field in cases of very high symmetry. But Gauss's law is actually quite deep. So I'll make some comments about that as we end the video. Or probably it's going to be some mixture of these two at the same time, Gauss's law and why we care about it. So let's start by trying to depict or draw a picture of some field lines. Here are some field lines, and they are piercing a surface whose name is S. So let's say there is a surface, and we'll call it S, and that surface has an area A sub s, right? So this is the area of the surface, and so to calculate the area, if this is like a rectangle, then we just need the height and the width, and we can calculate the area pretty easy. This is details about the surface. And then here is the field, and so field lines, you know, typically get drawn with little arrows depicting the flow. And you can see that this field is, so the field, because we're going to talk about electric field flux, we'll say that the field is E, that's the name that symbolizes this field. It pierces, I hope I spell this right, pierces or flows through the surface S. We say that the electric field has a flux phi through surface S. A quick way, or a summarizing way, to draw a picture of this situation is to maybe look at it from the side. So from the side, but you know that really this is sort of a three-dimensional issue, right? Electric field and electric force and charge have three-dimensional sort of presentations. But let's draw from the side. So here is the surface S from the side, and then you imagine the field E flowing or fluxing through S. Right, so this is from the side. We could have, so this could be a surface, say S sub A. So this is surface S sub A has the area S sub A, but we could, and here's S sub A from the side, but we could have, say, another surface who is getting pierced by, or has the electric field flux through it at angle other than pi over 2 radians, right? So you can see here that there seems to be a perpendicularity between the electric field and the surface, and over here instead these angles are not perpendicular. So so this flux through surface A and this flux through surface B, there are different issues on thinking about the flux depending on the angle. So what we're going to do is define the flux for simple case. So simple case, the electric field is uniform, which means same magnitude and direction everywhere. So that's what electric field is, uniform. And the electric field is perpendicular. So instead of always writing out perpendicular, which takes a little while to write, I'm going to use this symbol, this upside down capital T, is a sort of a mathy or geometric symbol for perpendicular, means 90 degrees, or pi over 2 radians. And E is perpendicular to S, so the surface S. So this kind of looks like this. So remember, in our field line diagram rules, the magnitude is represented by the density of the field lines, and the field lines, they all stay the same distance apart. So this represents that the field is the same magnitude everywhere. We may not know the magnitude, but we do know that it's uniform, that it doesn't change in field strength as we move around in space. The other thing is direction everywhere is the same. So everywhere I check, the field line points towards the right. So the direction is the same. That's what's meant by a uniform electric field. So E is perpendicular to S, is also an aspect of the simple case. So I don't know how to make little bullet points, so I'll just make bullet points with X's. So E is perpendicular to S everywhere, and also kind of on the side, but related, but it's actually already kind of stated up here. S is flat. So that is, S is not some curved surface like a piece of a sphere or something like that, but it's more like a piece of paper that doesn't have any bend in it. So S is flat. In this case, this very simple case, the flux is simply the magnitude of that vector times the area of the surface S. That's all it is. In more interesting cases, E is not perpendicular to S, which is the case I showed you where we had this surface we called B, but the flux was piercing at a not perpendicular direction towards it. So here's what we do instead. What we do is we define a vector that represents the surface S. So the way we define this vector, so this vector is often called n. It's not necessarily a unit vector, but it is a vector, and it is equal to the area of the surface S multiplying a unit vector n hat, where n hat is a unit vector perpendicular to the surface S. So it's got the area of S, but the direction of the vector is called n hat. So here is our surface, and the vector that I'm talking about is this vector here. This is the vector n, which in some sense defines or represents the surface S. So here it is, right? The length of the vector is just the area of the flat surface that is S. So it's area times the unit vector that points perpendicular to S. And the flux, in this slightly more complicated case, it's not just E times A, where everything is magnitudes here. In this case, we have to update what we mean. And the idea is we'll take the electric field, which we still are taking as the uniform electric field. So define flux for the simple case that E is uniform. So this is the overarching, so E is uniform for everything happening on this page. So E is uniform down here as well. And the idea is we'll use the dot product between the vector n and the electric field's value, which is the same everywhere. So I'm realizing that really, let me go back. I'm going to change something. Let's not do it like this. This is not how anybody does it. Let's define a vector called A that represents the surface. And it is the area of A, so that's just the size of the surface A, multiplied by n hat, where n hat is defined here. It's the unit vector perpendicular to S. And instead of writing the flux this way, because we no longer have an n vector, we have an a sub s vector. So the flux through the surface S is equal to the electric field dotted with the a vector that represents S. So this is a big deal. Up here, you can see that what's going to happen is I know that the magnitude of a sub s, the vector, is equal to just the area of the surface. And what's more is in the case where E is parallel, right? This is a symbol that means parallel to, so E is parallel to the vector a sub s if E is perpendicular to the surface S. I hope you can see this. Can you see this? And what I mean by seeing is not can you visually see this, but can you see this with your brain? Does your brain tell you that this makes sense? So E is parallel to a sub s in this first case. So here is the field. Here is the surface S, which is perpendicular to the field. But when the surface is perpendicular to the field, it has a vector called A. A is parallel to E, right? That's what I'm saying here. So in this case, right, you have to remember what a dot product does. So the dot product between parallel vectors is product of magnitudes. And so here, can you see this is a product of magnitudes? It's the simple case where the electric field is perpendicular to the surface. But that surface has a normal vector that will in turn be parallel to E. And so the vector that defines the surface or represents the surface will be parallel to the vector that represents the electric field. And then when you take the dot product between parallel vectors is only the product of magnitudes. And so the flux is just a product of magnitudes. So this is a special case of this. So in retrospect, maybe I should have just showed you this definition of the flux first, and then showed you that for a special case, you can just get product of magnitudes. Anyhow, you can, maybe you're going to learn from me waffling around and kind of being a little disorganized. It may be worth watching this video a couple of times, as well as comparing what you see here to stuff that you're reading in your textbook for your class. Okay, so I'm going to take this definition now, and I'm going to think a little bit about how I might use this. What if the surface S is curved? What normal direction, right? So normal means perpendicular. What perpendicular direction do we use to represent the surface S? The answer, we imagine S as a bunch, of tiny, so read infinitesimal in the calculus sense, surfaces. So what's this going to look like? So if S, let's imagine S is this surface. And if we walk around on the surface, like down in the center, this right here is a small piece of the surface. And over here is a small piece, and up here is a small piece. And up here, the normal vector is going to point something like this. Over here, the normal vector points something like this, and over here, the normal vector points something like this instead. And you can imagine tiling a whole bunch of small pieces of the total surface S, but every piece has a slightly different direction for its normal. And so what we'll imagine doing is if we have, so I should have drew this surface in red, but it's too late now. So imagine a flux coming up and piercing the surface, and look at the kind of field lines I'm drawing. I'm drawing field lines that are all interesting and curved. And so in this case, you can see that I have a E is non-uniform situation, and the surface S is curved. And so what we'll do in this case is we'll still imagine, what we'll do in this case is, for example, this little piece right here of the surface S is going to be considered a small vector, dA. So dA is a vector that represents a small part of S. And this small part has a small area which is equal to this vector's magnitude, like that, and the direction of the small area is just the perpendicular, right? So dA is equal to the small area, right, which is just the magnitude of itself, times n hat, where n hat is the local normal to the surface. So n hat is this red arrow for this part of the surface, but in this locality of the surface, this small place on the surface, n hat is this red vector instead, and n hat is this red vector instead for that small piece of the surface. So the little area element vector, so these are area element vectors, right? So these area element vectors are in general different, but the electric field is not uniform. So the electric field that goes through, what the value of the electric field at this small piece of surface, we can do a small piece of flux equal to the electric field at that location, which is not small in general. It's some macroscopic value, right? Some macroscopic field strength vector. And we'll dot product with the local surface element vector sitting right there. And that will be a small piece of flux. Up here, there's going to be some more small piece of flux. The electric field at that location dotted with the area element at the same location. And so these are small parts of the overall flux. So the total flux is equal to the integral over the surface, right? So we have to figure out what all the tiles of the surface are and add up all of the small pieces of flux. So we figure out some sort of variable to range over this surface, and as we range over the surface in an integral way with infinitesimal changes, we're going to add up the infinitesimal contributions to the overall flux. So this is how we're going to calculate the flux. It's the result of a dot product between a very, very small magnitude vector and a macroscopic field strength vector. Yeah. Okay, so that's the flux. Here's an example problem of calculating the flux of an electric field, given some information. So it says an electric field is uniform with the value 450 newtons per coulomb in the I-hat direction. As a drawing, I'm going to use rightward as the positive I-hat direction, so that's the x direction. An open surface S is a disk, so this is the drawing of the disk, and it has a radius of 12 centimeters. So I'm drawing this from the side. The field is going towards the right, and the disk is, you're seeing it edge on. So the plane of the flat disk is at an angle of 30 degrees to the electric field's direction. So these are the field lines of the electric field. And I'm indicating that there is an angle of 30 degrees between the plane of the disk and the field's direction. So that's the 30 degrees. And there are two questions for this setup. The first question is, what is the vector A that represents or describes the surface S? So S is this disk whose edge we're looking at. So we want to give a vector A. And the second part of this problem is, what is the flux? And the flux in this case is the flux of this field through this surface, which is a disk of radius 12 centimeters. So to do part A, you have to remember that the vector that represents the surface it's a vector that is perpendicular, right? So it is perpendicular to the plane of the surface. So that's the direction n hat that I indicated earlier. And then the magnitude that we use is just the area. So this is, so that, the area of a disk of 12 centimeters of radius. So the area is pi r squared. So it's pi times the radius, which is 12 centimeters, all squared. So this looks like 144 times pi times centimeters all squared. So this is what we're going to stick in front right there. So I'll just put area for now. So it's just the area times n hat. And n hat is this vector right there. So that's the area vector. So how would you build n hat? So this is just a unit vector, and I'm going to let you finish figuring out how to draw n hat. for this, what you'd have to do is decide which direction is the up-down. And so I've separated out and said that towards the right is what I'm going to understand as I hat. And most people probably would choose upwards as j hat. So the background coordinate system would look like this. So you could choose to do this. You need a vector of length 1 that points in the correct direction, right? So I'm going to put you do this. Okay, so part B is the question about flux. So, so this is what we have to do. We have to figure out what is the flux equal to. So you know that this is a Gauss's law chapter, but I can't use Gauss's law here. One of the things I don't know in order to use Gauss's law to figure out the flux, right? Gauss's law says that the flux is equal to the charge enclosed in a closed surface divided by epsilon naught. So one of the things is I don't know how to determine the charge. Nothing in the problem is telling me or giving me any information such that I could get the charge. I definitely know how to calculate, go look up epsilon naught. There's, no calculation to do. You just look up the value of epsilon naught. So Gauss's law says that this is how we would be able to calculate the flux. But we don't know we don't know the charge enclosed, so we can't do that. So we have to get the flux directly, and the flux is written this way. So you integrate over the surface of the electric field dotted with small area elements. But what we have is uniform E, right? So in the case of a uniform electric field, the flux is just equal to, actually we have two things that help a lot. So we have a uniform E and we have a flat surface S. So these two things make the flux super easy to calculate. It's just E dotted with the area vector A, and the area vector is here. So you might think that what we need is the answer to what is n hat, so that we can write down the full area vector A and figure out the dot product. But I'm going to show you that in this case you don't have to know how to write down n hat, although if you did know how to write down n hat, it's actually super easy to finish this problem if you already had n hat. But it turns out you don't actually need it. So let's bypass figuring out n hat. I'll let you finish that. And just go up and figure out how to do this directly. So, so this is, it's going to be the magnitude of the electric field, which is 450 newtons per coulomb, drop the I hat, right? No direction and magnitude, times the magnitude of the area. So the magnitude of the area is right here, actually. This is the magnitude of the area, right? This is also known as the magnitude of the area vector. And then I have to multiply by the cosine of the angle theta, where theta is the angle between the directions of E and A. So E is this way and A is this way. So this right here is the angle theta. So very carefully, this is not the given angle, right? So if you would have went straight in here and said, well, it's 450 newtons per coulomb times the area. So the area is pi times 12 centimeters squared. So that's that. And then if you write down cosine of 30, right, this is actually the wrong answer, because 30 degrees is not the correct angle. The correct angle actually is 60 degrees. 60 degrees, if you go and think about your triangles and angles and stuff going on in here, you'll find that the angle that you have to deal with is actually the 60 degree angle. So the answer really is 450 newtons per coulomb pi times 12 centimeters squared times the cosine of 60 degrees. This is the right answer. And when you go through and you calculate this stuff, it turns out that the answer is about 10.2. And the units, I will have converted from centimeters to meters squared, right? So centimeters squared up to meters squared. So the answer in newtons times meters squared per coulomb, not coulomb squared, sorry. It's per coulomb. So this is the answer to part B. You just have to put this in your calculator, change the units. You have to change the centimeter twice, right? Because, yeah. Okay. So let's talk about Gauss's law itself. Let me give you some setup. So the setup is this. Consider any arbitrary charge distribution. So any arbitrary charge distribution. It can be point particles, it can be shells of charge, rods of charge, and it can be a combination of all of them. So consider any arbitrary distribution of electric charges. Also, so that's one thing. Also, consider any arbitrary closed surface S. Okay, so here's an example of this setup. So here are some charges spread out in space, and here's a charged rod, and here is a charged conductor. Here's a charged cube. Just doesn't matter. There's just charge all over the place. So this is like Q1, Q2, Q3, etc. This is a rod. This is a cube. This is a conductor, right? So any arbitrary charge distribution. Now consider any arbitrary closed surface S. So actually, consider any arbitrary closed surface S. So let me just pick one. So I'm going to choose a surface S that happens to do something like the following. So it's closed. S is closed. That means that it does not have any holes. There's no gaps in S. It separates inside from outside, right? So that's what a closed surface does. It has a volume inside that's separated by the surface from a volume outside. Okay, so it looks like, let's finish labeling. So Q1, Q2, Q3, this one is number 4, number 5, number 6, number 7, number 8, number 9, and that's all the charges say. S encloses a list of charge. It encloses the conductor. It encloses 8, number 7, and also the cube. So everything, so these 4 charges, 1, 2, 3, 4, they're enclosed in S. So this is the surface S. Okay, so S excludes, so does not enclose Q1, Q2, Q3, Q4, Q5, and Q6, as well as the rod, as well as Q9. So those are excluded, right? So everywhere in this space is also electric field, right? And the electric field, you have to remember that we think of the electric field in, with the superposition principle, right? So that means that there is a net electric field, and it is equal to just the simple summation. It's the electric field of charge number 1 plus the electric field of charge number 2 plus dot 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 plus the electric field all the way up, right? 2, 3, 4, 5, 6, 7, 8, 9, the rod, the cube, the conductor. So let me just, of the point charges, there are 9 of them, so I've included them with this dot dot dot. And then we'll add the special ones. There is the cube, there's the rod, and there is the conductor. So this, the net electric field is actually, in this case, is quite complicated, right? But that's what the net electric field is. So Gauss's law says, so I'll just use a capital G, abbreviating Gauss's name. It just says this: if you were to integrate up the flux of the net electric field through S, right? So we have a surface and we have a net electric field everywhere, including at places on the surface. So you calculate the electric field flux of this net electric field through the arbitrary surface S. You are guaranteed that when you go through the process of calculating up this flux is this integration. You will only ever get the Q enclosed in S divided by epsilon naught. So in this case right here, it's the sum of those 4 different amounts of charge. It'll be, so in this case, the flux of the net electric field through our surface S will just be the charge on the conductor plus point charge 8 plus point charge 7 plus the charge on the cube. Divided by epsilon 0. Yeah, so this is sort of a generic description of Gauss's law. Of course, this thing right here is usually extremely difficult to calculate, right? This integral is super difficult, especially if I have this really strange electric field. This net electric field is weird, and I have this like crazy shaped surface. So this is usually too difficult to calculate directly. But what Gauss's law does is it says, well, you don't actually have to calculate that if you can count up the charge, for example. So counting up the charge is sort of easy if you know the values, right? Maybe that would be given in a problem. So this is what Gauss's law says. What's interesting is to sort of pick this apart a bit. So you know that E net is equal to E from charge number 1 plus dot 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 all the way up to E from charge number 9 in this case, plus the cube's electric field plus the rod's electric field plus the conductor's electric field. In this example, that's what the net electric field is. I'd like to show you that this can be put in to the integral, right? So I integrate over the surface S, arbitrary surface, and really it's the same thing as the integral of Q1's flux through S plus the integral of Q2's flux through the same S plus dot 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 the integral of the cube's electric field through S plus, right, etc. That is, I can consider just the flux of electric field due to the individual charges, like this. Okay, so with that said, let's use Gauss's law on a single point charge. So here's the single point charge. Let's say it's of charge Q. And here is somewhat of a depiction of the electric field of Q. Right, this is the electric field of Q. Since there is only one charge in this universe, so another word for this universe is this thought experiment. So since there is only one charge in this thought experiment, the electric field due to the point charge Q is the net electric field. That's what it says, right? So this is the superposition principle when there's really only one source of field, one point charge Q. So that's the net field. So let's, so I've definitely got this electric field. You've worked with it already. And let's consider arbitrary surface S. So here is, let's draw this as our surface S1, right? So we're going to do a couple of surfaces. Here's a surface S1, and here is a closed surface S2, right? It's not important that S2 is not overlapping with S1. It doesn't really matter. I could have drawn S2 to overlap with S1. But in particular, I really wanted S2 not to include the charge and S1 to include the charge. So I know that, so let's use Gauss's law twice. Here is Gauss's law for S1, and I'll do Gauss's law for S2 over here. So the flux of the electric field through the surface surface S1, in this case, the enclosed charge inside of S1 is all of Q. It's Q over epsilon 0. Yeah, and that's what I have. If I look at the electric field dotted with area elements over S2, though, it's equal to Q enclosed in S2 divided by epsilon 0, but the Q enclosed in S2 is 0. Whereas this one, if we genuinely have a point charge in there, this is not 0. So I've got 0 here and not 0 there. So this is not 0. So these two surfaces have different fluxes.
Gauss's law is telling us they'll have different fluxes. Okay, so why is the question here? So why is it 0 here and why is it not 0 there? Because if you look at S2, S2 has electric field going into the surface here and electric field going into the surface there. S2 also has electric field piercing out of the surface there and piercing out of the surface there, right? So that's what's happening on S2. So in S2 has both flux into and out of, right? In and out. S1 has only flux out. So not only is this not 0, but it's actually, we can say a little bit more. It's not 0, but also it's actually positive, right? You might say that in this scenario, the flux is positive, right? So the flux is positive. And the flux is positive. Here we have flux leaving the surface. Here we have flux leaving the surface, but we also have flux going into the surface. So the question is, does this mean that if you flux into the surface, you have negative flux, and if you flux out of the surface, this is considered positive flux? And the answer is yeah, that's exactly. So whenever the field lines go into the surface, like from the outside to the inside, you consider that a negative flux. And when the field lines go from the inside to the outside instead, that's called a positive flux. And what happens with Gauss's law, what Gauss's law guarantees us, is if the charge is on the outside of a closed surface, then that charge's field lines will flux both into and out of the surface in such a way that the fluxes in will always cancel against the fluxes out. So that's the sense in which we get no flux at all. Over here we have a positive flux. If you think of a negative point charge, here's a negative point charge, the field lines are different than the positive point charge because the field lines go into negative charge, right? That's how we draw field line diagrams. A positive point charge feels a force attracting it towards the minus, whereas a positive test charge feels a force repelling it from that positive point charge in the middle. So if you go in and you draw a surface, say just S like this, we've got flux that goes into the surface everywhere. So this is in. These are all inwards flux. Flux, or small pieces of flux, are always inwards, which is the same thing as saying negative. So overall flux of this electric field through this surface S right here is going to be less than 0, and Gauss's law tells me, well, it's the charge enclosed over epsilon naught, and this charge, if this one is called Q, then this one is called minus Q. And so the charge enclosed is minus Q over epsilon naught, and this kind of a quantity is less than 0, so they match right there. So when field lines go into a surface, this is negative flux. And when they go out of a surface, this is positive flux. All right. So really quickly, dA. So if I have a surface, say, right, let's study a small surface element. So here is, in some sort of range variable, here is a small tile that I'm going to represent with this arrow here. So this is the dA vector at this location on some arbitrary surface S. And let's imagine that I have a positive charge, say over here. So here is a positive charge. And at the location of the little area element of our surface, this positive charge has this electric field vector. That's the electric field due to this positive charge over here, right? Because the field line goes like that across the page, and there's an arrow indicating that positive charges get forced in that direction. So because of this point charge, there is this electric field. So I'll put, it's the electric field due to this point charge over here. And you can see that this angle, right? This angle right here is greater than 90 degrees. So why is this interesting? It's interesting because when I go and there are small contributions to the total flux through this surface S, which are equal to the electric field vector at that place on S, dotted with the area element vector that represents that small piece of surface on S. And if you look at this, this is E magnitude times the magnitude of the small area element, dA, times the cosine of the angle between them. And the cosine of theta is negative when theta is bigger than 90 and less than 180. Right? Actually, less than 270, excuse me. Which is kind of funny. It's like saying that we can consider electric field vectors that point all through this 180 degrees from 90 to dA to 270 to dA, which is also known as 90 from a different person's point of view. But anyways, the cosine is going to be negative. So that means that the small contribution to the flux of an electric field that goes into the surface, which is backwards to the area element that points outwards from the surface, then the small contribution to the flux will be less than 0. So as you integrate up the small contributions to the flux, you can get negative contributions and you can have positive contributions. You can also have 0 contributions when the angle theta is 90 degrees. So those are perpendicular situations. Okay, so this is Gauss's law. Yeah, I think I drew enough pictures and said some stuff about positive flux and negative flux. Okay.